From the deepest stillness of a desert night, we gaze upward. The cosmos presents itself as a tapestry of serene consistency, an endless diamond-dusted black, impartial and eternal. For centuries, this apparent uniformity has been a cornerstone of our cosmic understanding. It whispered a comforting truth that here on this small orbiting rock we are not special, that the grand architecture of the universe would look the same from any vantage point. But the most profound discoveries often begin not with a bang, but with a whisper, a subtle discrepancy, a note slightly out of key in the grand cosmic symphony. Modern astronomy has gifted us with eyes to see the universe's infancy, to look back across 13 billion years to its very first light. And in that ancient glow we have found something that should not be there, a colossal shadow, a region of inexplicable cold stretching across 1 billion light-years. This anomaly has led us to a staggering, almost heretical proposition. What if the uniformity we see is a local illusion? What if our home, our Milky Way galaxy and all its neighbors is adrift within a vast anomalous structure, a bubble of near-nothingness, a cosmic underdensity of unimaginable scale? And if we are inside this void, then everything we thought we knew about our place in the cosmos is wrong. We are not in a typical corner of the universe. We are in a profoundly strange one, and its existence changes everything. To grasp the magnitude of this cosmic revelation, we must first journey back. We must appreciate the towering intellectual edifice it seeks to challenge. For millennia, humanity placed itself at the very heart of creation. The Earth was the fixed stage upon which the celestial drama unfolded. This was a universe of profound importance built for us. Then thinkers like Copernicus and Galileo dismantled that stage piece by piece. They set our world in motion, revealing it to be just one planet among many, orbiting one star among billions. This demotion gave birth to a powerful scientific idea, the Copernican Principle. It proposes that there is no privileged location in the universe, no center, no edge, no special direction. The cosmos on its largest scales is fundamentally the same everywhere. This principle of mediocrity became the bedrock of modern cosmology. It was woven into the very mathematics of Albert Einstein's theory of general relativity. When he first applied his revolutionary equations to the universe as a whole, they predicted a dynamic cosmos, a universe that must either be expanding or contracting. This idea was so unsettling, so contrary to the prevailing wisdom of a static, eternal cosmos, that Einstein himself faltered. He introduced a fudge factor, the cosmological constant, to force his universe to stand still, a decision he would later call his greatest blunder. The proof of a dynamic universe would come not from a theorist but an observer. In the 1,920 seconds from his perch atop Mount Wilson in California, Edwin Hubble undertook a meticulous survey. He was measuring the light from distant smudges, then called spiral nebulae. He discovered that the light from almost every single one of them was stretched, shifted toward the red end of the spectrum. This redshift was a telltale sign of the Doppler effect, the same phenomenon that makes an ambulance siren drop in pitch as it speeds away from you. Hubble realized these nebulae, which were in fact entire galaxies, were all rushing away from us. And more profoundly, the farther away a galaxy was, the faster it was receding. The universe was not static. It was expanding. This was not an explosion of galaxies times through times space like shrapnel from a bomb. It was an expansion times of time-space itself. The most elegant analogy to grasp this concept is that of a loaf of raisin bread rising in an oven. Imagine you are sitting on one raisin. As the dough expands, you would see every other raisin moving away from you. A raisin twice as far away would move away twice as fast because there's twice as much expanding dough between you and it. Crucially, no matter which raisin you were on, the view would be identical. There is no center to the expansion. Every point is moving away from every other point. This was the Copernican Principle made manifest in the motion of the cosmos. Our galaxy, the Milky Way, was just one raisin among countless others in the rising loaf of space-time. A universe expanding in this uniform way implies a startling history. If we run the cosmic movie in reverse, all the galaxies rush back together. Space contracts and the universe becomes hotter and denser. Rewind far enough, some 13.8 billion years, and everything we can see is compressed into a single infinitesimal point, a state of unimaginable heat and density. This was the genesis of the Big Bang theory, a theory that made a stunning prediction. In its youth, the universe was a blindingly hot, opaque fog of plasma. After about 3,800,000 years, it cooled enough for atoms to form. At that moment, the fog cleared. Light was set free to travel across the cosmos for the very first time. That first light, stretched by 13.8 billion years of cosmic expansion from blistering gamma rays into cold, faint microwaves, should still be detectable today. It should permeate all of space, a faint residual hum from the dawn of time. In 1964 at Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were trying to calibrate a large horn antenna. They were plagued by a persistent, low-level hiss, a noise that came from every direction, day and night, through every season. They checked their equipment, rewired their systems, and even cleaned out what they delicately termed a white dielectric material. It was pigeon droppings, but the hiss remained. It was an immutable feature of the sky itself. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was building a detector specifically to search for the predicted afterglow of the Big Bang. When the two groups finally connected, the truth was revealed. Penzias and Wilson had accidentally stumbled upon the most profound discovery in cosmological history. They had found the echo of creation, the cosmic microwave background, or CMB. This ancient light is a baby picture of the universe. It shows us what the cosmos looked like when it was a mere infant, and according to the standard model of cosmology, that picture should be almost perfectly uniform. The temperature of this light should be the same across the entire sky. Not perfectly identical, but close. There must be minuscule variations, tiny fluctuations in temperature and density, representing the seeds from which all future structures, galaxies, stars, and planets would eventually grow. These fluctuations would be the equivalent of finding a difference of 1 part in 100,000, like detecting a single grain of sand on a vast, smooth beach. For decades, we built more and more sensitive instruments to map this ancient light. First, the Cosmic Background Explorer, or COBE satellite. It produced a map showing the predicted tiny hot and cold spots, a triumphant confirmation of the Big Bang model. Then came the Wilkinson Microwave Anisotropy Probe, or WMAP. Its map was vastly more detailed, a stunning Rorschach blot of primordial energy. It was in this exquisite image of the infant cosmos that the first serious crack in our understanding appeared. Among the random seeming mottling of hot and cold spots, one feature stood out, or rather, failed to stand out. In the direction of the constellation Eridanus, there was a patch of sky that was abnormally large and abnormally cold. Imagine scanning a satellite image of the Earth's oceans. You expect to see waves of all shapes and sizes, a chaotic random pattern. Now imagine finding a single perfectly circular patch of ocean 1,000 miles across that is mysteriously and unnervingly calm. That is the scale of what we saw in the CMB. This cold spot was not just a little colder, it was far colder than the random fluctuations should allow. and it was immense, spanning over 1 billion light-years of space. Initially, cosmologists assumed it was an instrumental error or a statistical fluke, but as the data was refined and then confirmed by the even more precise Planck satellite, the cold spot refused to go away. It stared back at us from the dawn of time, a defiant anomaly. The odds of such a feature appearing by pure chance in the standard model of the universe are less than 1 in 1,000. It was a blemish on our otherwise perfect picture of the early cosmos. A deep fundamental mystery that demanded an explanation. And the search for that explanation would lead us away from the distant past and into our own cosmic backyard. While some cosmologists were staring deep into the past at the CMB, others were mapping the present-day universe. They were plotting the positions of hundreds of thousands of galaxies. Their work revealed that galaxies are not scattered randomly through space. They are organized into a magnificent filigreed structure known as the cosmic web, vast chains and filaments of galaxies separated by immense dark chasms of near-nothingness. These chasms are known as cosmic voids. They are the largest structures in the universe. Imagine flying through the cosmos. You would spend most of your journey in profound emptiness. Then, for a time, you would soar through a brightly lit supercluster, a metropolis of galaxies, before plunging back into the dark. These voids are not entirely empty, but they are dramatically underdense. They contain far fewer galaxies, less gas, and even less dark matter than the cosmic average. In 2013, a team of astronomers led by Amy Barger, Ryan Keenan, and Lennox Cowie were studying this cosmic web. They weren't looking for anything in particular. They were simply creating a more accurate map of our local galactic neighborhood. What they found was astonishing. Our own Milky Way galaxy appears to be situated deep inside one of these enormous voids. It is not a small one. This structure, which has come to be known as the KBC Void, is a bubble of low-density space, roughly 2 billion light-years in diameter. It is the largest cosmic void ever discovered. By some estimates, our region of space has only about half the density of the universal average. We are not living in a typical bustling cosmic metropolis. We are living in the remote, sparsely populated cosmic countryside. For a time, the CMB cold spot and the KBC void were seen as two separate, unrelated cosmological curiosities. One was a feature from the distant past, imprinted on the first light of the universe. The other was a feature of the present-day structure of the local cosmos. But then, a radical idea began to take hold. What if they were not two mysteries but two sides of the same coin? What if the cold spot in the ancient light was not a primordial feature at all? What if it was an illusion, an artifact created by the giant void we are living inside today? This hypothesis hinges on a subtle but powerful effect of general relativity. It's called the integrated Sachs-Wolfe, or ISW effect. To understand it, we must follow the journey of a single particle of light, a photon from the CMB. For 13.8 billion years, this photon has been traveling across the universe to reach our telescopes. Along its way, it crosses vast structures, dense galaxy clusters, and empty voids. When a photon enters a dense region like a cluster rich in dark matter, it falls into a gravitational well. It gains energy, becoming slightly hotter or bluer. As it climbs back out of that gravitational well, it loses the exact same amount of energy, returning to its original temperature. In a static universe, the net effect would be zero. But our universe is not static. It is expanding, and that expansion is accelerating due to dark energy. Now consider a photon crossing a massive supervoid. As the photon enters the void, it falls down a very shallow gravitational hill, losing a small amount of energy and becoming slightly colder. While it is traversing the immense void, a journey that can take billions of years, the universe continues to expand at an accelerating rate. The void itself stretches and becomes even less dense, its gravitational hill even flatter. So when the photon climbs back out, it has a much shallower hill to ascend. It doesn't regain all the energy it lost on the way in. The net result is that the photon emerges from the void with slightly less energy than it had when it entered. It has been permanently redshifted, appearing to us as fractionally colder. The giant void acts as a cosmic refrigerator for the light passing through it. Here, then, is the breathtaking proposal. The CMB cold spot is not a real cold patch on the surface of last scattering. It is an optical illusion. We are looking out at the CMB in all directions. In most directions, the light has had an average journey, but in the direction of the constellation Eridanus, we are looking out through the longest possible axis of our own local void. The photons from that specific direction have had to travel through the heart of this colossal energy-sapping underdensity. Their energy has been drained by the ISW effect more than light from any other direction. They arrive at our telescopes, appearing abnormally cold. The cold spot is a shadow cast by our own empty home. This one elegant idea solves two of cosmology's most persistent puzzles in a single stroke. It explains the anomalous cold spot in the CMB without resorting to new exotic physics, and it accounts for the strange, underdense nature of our local cosmic environment. But its implications are far more profound. It would represent the most significant challenge to the Copernican Principle in 500 years. If this hypothesis is correct, we are not mediocre observers in a typical location. We are living in a cosmic anomaly, a 2 billion light-year-wide bubble of relative emptiness. Our view of the universe is fundamentally skewed, and this skewed perspective might just solve another major crisis in modern cosmology, the troubling case of the Hubble tension. For the past decade, a quiet crisis has been brewing in the heart of cosmology. Scientists have two primary methods for measuring the expansion rate of the universe, known as the Hubble constant. One method involves looking at the very early universe. By studying the precise details of the fluctuations in the cosmic microwave background, scientists can use our standard model of cosmology to predict what the expansion rate should be today. It's like studying the DNA of an infant to predict its adult height. This method gives a value of about 67 kilometers per second per megaparsec. The other method involves looking at the local universe. Astronomers measure the distances and recession velocities of relatively nearby galaxies and supernovae. It's like measuring the adult's height directly with a tape measure. This method consistently yields a higher value, around 73 kilometers per second per megaparsec. The two measurements are both incredibly precise, and their error bars do not overlap. They are in fundamental disagreement. The universe appears to be expanding faster today than its own baby picture suggests it should be. This discrepancy, the Hubble tension, has led some to suggest that our standard model of cosmology is broken, that we are missing some fundamental ingredient, perhaps a new type of particle or a novel form of dark energy. But the giant void hypothesis offers a much simpler and perhaps more startling solution. If we live inside a massive underdense bubble, it would directly affect our local measurements. The KBC Void, being far less dense than the rest of the universe, exerts a weaker gravitational pull. Think of it as a cosmic valley in the landscape of space-time. Galaxies on the far side of the void are being pulled away from us by the denser, more massive universe beyond the bubble's edge. Meanwhile, there is less matter times inside times the bubble to hold things back. The result is a local outflow, a kind of cosmic river flowing out of the void. When we measure the expansion rate using nearby galaxies, we are measuring this combined effect, the global expansion of the universe, times this local outflow. Our measurement is biased. It appears artificially high. The measurement from the cosmic microwave background, on the other hand, reflects the true global average expansion rate of the entire universe. The Hubble tension in this scenario is not a tension at all. It is the direct, measurable consequence of our anomalous position in the cosmos. The two numbers are different because they are measuring two different things: the local expansion rate inside our bubble and the global expansion rate outside of it. Our address in the universe is the missing piece of the puzzle. This is a powerful and compelling narrative. It ties together disparate observations into a coherent, if unsettling, picture. But it is not the only possible explanation on the table. Science thrives on skepticism, on the rigorous testing of alternative ideas. One strong counterargument is that this is all just a grand coincidence. The universe is vast, and in a large enough dataset, rare statistical flukes are bound to happen. Perhaps the cold spot really is just an unusually large primordial fluctuation, and perhaps it is just by pure chance that we happen to live inside a very large void. The correlation between their positions in the sky could be nothing more than cosmic happenstance. Many cosmologists still favor this view, clinging to the foundational comfort of the Copernican Principle. To abandon it is to open a Pandora's box of complexities. If our local measurements are biased, how can we ever be sure we are measuring the true properties of the universe as a whole? Other, more exotic theories for the cold spot remain in play. One of the most tantalizing is the idea of a multiverse. In this picture, our universe is but one bubble in an endless foam of other universes, each with potentially different laws of physics. The cold spot in this scenario is a bruise, the remnant of a gentle collision between our universe and another bubble universe in the distant past. This cosmic fender bender would have left a scar, a region of altered energy density, which we now see imprinted on the CMB. Another possibility is that the cold spot is a topological defect, a flaw in the very fabric of space-time. Imagine water freezing into ice. Sometimes imperfections or cracks can get locked into the crystalline structure. Similarly, as the infant universe went through a rapid series of phase transitions, it's possible that a remnant from an earlier, more chaotic phase, a cosmic texture, was frozen into the cosmos. This scar tissue would disrupt the CMB light passing through it, creating the illusion of a cold spot. These are fantastic, mind-bending ideas pushing the boundaries of known physics. But the void hypothesis has one distinct advantage: it is testable right now. The final verdict will come from our next generation of cosmic cartographers. Telescopes like the Euclid Space Observatory are currently undertaking the largest, most detailed 3D survey of the universe ever attempted. They are meticulously mapping the precise locations of billions of galaxies. Their data will allow us to confirm the existence, shape, and scale of the KBC Void with unprecedented accuracy. We will be able to determine if it is truly large enough and empty enough to produce the full effect of the CMB cold spot, and we will see if it's truly centered on us as the hypothesis would predict. Simultaneously, new surveys using the James Webb Space Telescope are refining our local measurements of the Hubble constant. If the void hypothesis is correct, we should find subtle variations in the expansion rate depending on the direction we look. Anisotropies in the Hubble flow that reflect our off-center position within this great cosmic bubble. The evidence is accumulating. Each new dataset seems to add another piece to the puzzle, strengthening the case for our peculiar cosmic address. What began as a strange cold anomaly in a map of ancient light is becoming a potential revolution in our understanding of ourselves. We are being forced to confront the possibility that the universe is not as simple as we had hoped. For 500 years, science has been a story of cosmic demotion. We are not the center of the solar system. Our sun is an average star in an unexceptional galaxy. We have embraced our mediocrity, but this new picture suggests a different kind of specialness. Not the specialness of being the singular focus of creation, but the specialness of being an outlier, an anomaly, a resident of a rare and unusual cosmic structure. It does not restore us to the center, but it does place us in a context that is fundamentally different from the norm. It means our view from this planet, this solar system, is unique, a biased perspective that we must carefully account for in all of our cosmic calculations. We look up at the same sky our ancestors did, but we see it through new eyes. We see not just points of light, but the faint outline of our own invisible home. A 2 billion light-year wide bubble that separates us from the wider, denser, and perhaps more normal universe beyond. We are castaways adrift in a sea of relative emptiness. The quest to understand our place in the cosmos has taken us from the center of all things to the quietest of backwaters. And in this strange, empty corner of the universe, the greatest mysteries still await. Our journey is not about finding our way back to the center. It is about learning to read the map from the strange and wonderful place we find ourselves.